It's something we do every single day, pretty much without thinking about it, that satisfying click of a power button. But behind that one simple press, there's this hidden world, a silent symphony of electrical signals that brings a complex machine from, well, being completely off to totally alive and interactive. So let's pull back the curtain and see what's really going on in that first critical second.
So let's really think about it for a moment. You hit the button, and in a few seconds, a logo pops up on the screen. But what really happens between that physical touch and the very first pixel lighting up? It's this incredibly fast and precise dance between hardware and software, a process that's so fundamental to how things work that we almost never stop to question it. Today, we're going to follow that journey step by step.
All right, so here's our game plan. We're going to start with the very first electrical spark. Then we'll follow this cascade of power that wakes up all the hardware. We'll see the exact moment the system's brain, the processor, comes online. Then, we'll walk through the system's own health check, watch it pass its final exam, and finally, witness that crucial handoff that brings your operating system to life. It all starts right here. Before anything complicated can happen, the system needs to be 100% sure of one thing. It has a stable, reliable source of power. And this isn't just about being plugged into the wall. It's about the internal parts confirming that the voltage is right and the current is steady. This is really the foundation that everything else is built on. Okay, so now think of what happens next like a perfectly set up line of dominoes. One can't fall until the one right before it does. This is the power sequence, and it's this meticulously designed chain reaction. Why is it so rigid? Well, because turning on sensitive components in the wrong order could literally fry them. So if any single one of these steps fails, the whole process just stops to protect the hardware. So what are these dominoes? Well, first, the system confirms it's getting good power from the adapter. This wakes up a small, dedicated chip, often called an embedded controller. He's the real unsung hero of the startup process. When you press the power button, this is the chip that gets the signal, and only then does it give the green light to turn on the main system power. Think of these as the electrical highways for the whole motherboard. The very last domino in this chain is enabling the specific voltage needed by the brain, the central processing unit, or CPU. With power now flowing exactly where it needs to, we get to this really huge moment, waking up the brain of the whole operation. The CPU has been totally dormant, but now that its power is stable, it's ready to stir. But it can't just wake up all on its own. It's waiting for one final, all-clear signal. And this is basically a critical handshake. It's a two-part confirmation that has to happen. First, the main system sends out a system power OK signal, which is like it's shouting, hey, all the big components have stable power. At the same time, another signal confirms CPU voltage OK. Only when the processor gets both of these all-clear signals can it actually start to do its job. Now, before we see what the CPU does next, we gotta understand this key concept, the bus. The easiest way to think about it is like a superhighway system inside your computer. It's a bunch of electrical pathways that lets the CPU, the memory, and everything else talk to each other. Without this highway, the CPU would be awake, but totally isolated, unable to send or receive a single piece of information. And this is the very first thing the CPU does. It wakes up and immediately reaches out onto that information highway, the system bus. It's not doing anything complicated yet. It's really just asking a question. It sends a signal out to a very specific, predefined address, basically looking for its first set of instructions, the firmware that's going to guide it through the rest of this whole startup process. So once it finds those instructions, the system goes into this critical diagnostic phase. It's called the power-on self-test, or POST. Honestly, you can think of it like a computer's morning routine. Stretching, making sure all its arms and legs are working, and just getting ready for the day. It's a methodical checklist to make sure all the core hardware is there and actually working. So how does it keep track of this checklist? With something called POST codes. Every time the system finishes a step, it sends a little code to a special diagnostic port. For an engineer trying to figure out what's wrong, these codes are everything. They're like reading a patient's vital signs. If the machine doesn't start, the very last code it sent tells them exactly where the process failed. It's an absolutely essential tool for debugging. All right, let's look at what's on this checklist. The very first checks are for the absolute essentials. It starts by loading microcode, which is kind of like a tiny software patch that fine-tunes the CPU itself. Then, it resets the main system controller back to its factory defaults to make sure it's starting from a clean slate. And finally, it kicks on the real-time clocks, which are crucial for keeping everything else in sync. Next up is one of the most vital components, the system memory, or RAM. The routine first clears out a small initial chunk of memory. Then it does some simple read and write tests on that chunk just to make sure it works. Once that passes, it starts the process of sizing, or just counting up, all the memory that's installed in the system. And this can actually be one of the longer parts of the whole post sequence. Okay, so the core stuff, the CPU, the main controller, the memory, it's all been verified. Now the system starts to look around a bit. It's time to check on all the other devices plugged into it. This is basically a roll call, making sure every single peripheral is present and accounted for before the main event can begin. And this slide just lays out that roll call perfectly. The system methodically tests the keyboard controller, then it checks the direct memory access channels, which are like high-speed lanes that let your storage drives talk directly to memory without bothering the CPU. Then it initializes the controllers for your hard drives and starts waking up the USB ports. Every successful check is another passed test on its final exam.
So at this point, the hardware is pretty much done. Its job is finished. The power is stable, the core components are checked, the peripherals are awake and ready to go. The entire low-level system has passed its own self-test. Now it's time to pass the baton to a much, much bigger and more complex piece of software.
And here we are, at the climax of the whole journey. This initial firmware, the program that has guided this entire process so far, is about to make itself obsolete. Its one last job is to find the operating system on a storage drive and give it complete and total control of the hardware.
So how does this handoff actually happen? Well, a lot of systems will give you a little beep to let you know the post was successful. The firmware then runs a boot routine, searching your drives for one that has an operating system. When it finds one, it executes a special final command, a sort of digital flare. In engineering terms, this involves a specific system command, an interrupt, that's essentially the firmware's explicit instruction saying, "My job is done, you're in charge now."
And just like that, with that one command, the silent symphony is over. The low-level boot process is finished. That familiar loading screen of your operating system appears, and from this moment on, a completely different, much more complex software program is running the show. And all of this, from pressing the button to this handoff, happened in just a few seconds. We've just walked through a perfect startup. But in this incredibly complex and delicate dance of signals, where a single incorrect voltage or a bad connection for just a split second can stop everything, it really makes you wonder, right? Where does this whole thing usually go wrong? What's the most common point of failure? Is it that initial power sequence, the memory check, or something else entirely? That's something to think about the next time you press that power button.